Good morning, everyone, and good afternoon, good evening for everybody who joined virtually from different places. Thanks for coming. And first of all, I want to thank the leaders who sent me here to share the work we have done about the explainability to the whole open source community. Here's a good venue for that. So my talk today is about kind of X-FIPE. X-FIPE stands for Extended Feature Impact for Prediction Explanation. So I want to start with two questions. So would you like to convince your business users to adopt your predictive models? A second one is, would you like to include a computationally efficient and a theoretically sound explainable AI in your machine learning workflows? So hello, everyone. This is Xingdei Jiang. I'm a machine learning engineer from Humana, where we build machine learning platforms, serve over 300 data scientists, and serve more than 8 million consumers. So a word about Humana. Humana delivered the human care. So a few things I want to highlight about Humana here. So the strategy there is we want to bring increase people's health, make people healthier in a simpler experience. So to do that, we have equitable AI, and also we have a team dedicated to that. So to deliver the human care relies on aligning the actions and the behaviors to build trust with our members. So here I highlighted 3 parts. And next one, this one is specifically a system where I'm part of to build. It's called machine learning platform. We are leveraging its multi-sided platform ecosystem to accelerate the value creation. So in here, in terms of the platform, I mean the consumers and the producers. So I'm focusing on the last part, the lower part, which is the MLP part, where our producers are data scientists, our consumers are our clinicians, care managers, and associates. And ultimately, we want to serve the needs of the consumers, to bring everything to consumer, make their life healthier, and make their experience simpler. And in MLP, we are performing doing the ethical way where the 6 AI principles are observed. Specifically, we want to do that reliable and fairly and transparent, and also we want to keep the security and privacy, and also we know who is accountable for which. So that led to today's talk. The talk is about an algorithm, about a model explainability. In this talk, I will use the interpretability and explainability interchangeably. There are differences between them. I have reference at the end so that you can look into that to get more about that. So the data agenda have 4 parts. First, so why the explainability matters. And the second part is what are one example. We call that top drivers in our industry. The third part is I want to compare what is out there. The fourth part, I want to dive deep onto our X-FIPE. I want to highlight 2 things, computationally efficient and theoretically sound. First of all, why it matters. It doesn't matter until just a few years ago. I did a Google Trend search, explainable AI, actually trending upwards just for the last couple of years. I remember yesterday's talk from Dr. Peter Norvig. He said we have moving from model-centric, data-centric, into somewhere we would like to find what is the objective function we want to optimize. So one of the topic he mentioned is ethics. I think we have been doing a little bit of work on that. And also to echo what Dr. Andrew Ng, the message on the keynote as well, we are building that in our vertical at healthcare. So I want to emphasize the importance and the whys using one word. That will be the trust. If I want to use a sentence to do so, that will be the interpretability is vital for business stakeholders to adopt ML, machine learning, to serve consumers in compliance with rules. So I highlighted 3 parties before. This one I did not. So here you can see 4 parties are involved here. The first one, like us, who are doing the data science and the AI researchers. We can use model explainability to do a few things. We can do the debug, and so that we can improve and also check for biases. And in order for the model, so we can build the model we can, no matter how accurate it is, it won't deliver value until the business stakeholder adopts it. So in order for a model to provide its value, we need the business stakeholders to trust and adopt our model, essentially to put our model into production. So for a customer-centric company like Humana, the ultimate goal is to let the consumer to trust the business and have a good health and have a better experience. So we need to explain to them about the rules or underlying things in the most simple way. So last but not least, which is the last part, we need rules. In our industry, the HIPAA is one of them. And also, the last year or 2, we have joined called Equal AI Pledge. We want to do things without bias and do that in a fair and responsible way. So I will give you an example in our healthcare industry. So here you see the scores for different personas. The first one is 0.99, 0.85, and 0.4 for the third one. So that is a risk score of our model to predict someone's likelihood to go to a hospital. So we can tell what the risk factors are presented in each specific patient. So for example, the first one is mainly the utilization driven. So look at a little bit closely, maybe not that large, but the first one has the ER visits and some of the costs related to the ER, which is emergency room. And you look at the second one is similar to the first one. It's utilization driven, but it's more towards the COPD, kind of respiratory condition driven. So it has a lot of costs and the visits related to the respiratory conditions and disease. The third one is a behavioral condition driven. You see, like anxiety, stress. So if we treat everybody, just look at the score, and we'll have one solution. But if you look at that in a local level, what I mean by local is for each specific members, and you see what is their reason, what is a driver for them to have such a high risk score. With that, so our care managers can reach out to them and with a specific message we have to drive the conversation, also direct them or triage them to a specific avenue down the road, so that that will keep the consumer in a healthier, relatively healthier way. The next part is I would like to talk a little bit about the algorithms we have already on the market. I think we know a lot about LIME and SHAP in this audience, I believe so. Show me your hand if you know. Yeah, a lot of them, you know all of them. The LIME is local interpretable model agnostic explanations. What it does, if you look at the equation, what you want to optimize is 2 things. First of all is the L part, the loss. The second part, the omega part, is a constraint on the G. The G is from a capital G, the family of explainable models, where you want to approximate the F, which is your model. You want to minimize the summation of the loss between the F, the original model, and the model you would like to approximate, like the G here, within a vicinity of the pi x. The pi x is called kernel. And the second part is you want to minimize the complexity of the G as well. That's why it's a two-part optimization. That is pretty good and have good use for the open community, has a lot of likes and stars on GitHub. And the second part is about the SHAP. It's called a Shapley Additive Explanations. This one is a unified framework. If you look at the equation there, we have the phi 0 and the plus and the summation of all others. So what's important about the z's? Z's are the ones you see here is either 1 or 0. That means you choose or not choose. M is a number of the features, the input features. So what that does is to try to make a black or non-transparent models on the left and output a explainability for them. So give us the impact for the age and all other factors. So essentially what SHAP does is to put a complex, a hidden or non-transparent model and build an explainer on top of that so that we can make that transparent and explain that. So all of them are great resources. I have learned quite a lot built on them. And why there is more? So here I want to do a comparison about those methods. So here I list out the 6 dimensions. The 6 dimensions, I would like to highlight 2. The first one is computational efficiency. This one I'm using the running time. And the lime is pretty high, and medium or high. The SHAP is pretty high, and so it's a 5, which is our work is built on, and also the X-FIPE is extended 5. So I have a comparison using a 500K observations and about 100 plus features. The 5 was taking about 5 minutes, and the SHAP about 30 minutes. The lime, our colleague did not get results after a few hours. So the X-FIPE actually even faster. That will be highlighted in the next few slides. The second part I would like to highlight is the number 6, is a Python or Spark model agnostic. And the SHAP and the lime support all of them, both of them, and the SHAP supports the tree models of Spark models. But if you look at the SAR, there's an open issue. It says, I think from 2018, said, do we have a Spark version in plan? I don't think that is close yet, so it's still open. If you want to learn about the 5, which is the foundation of our extended version of that, you can look at that link below. And it is written by colleagues of mine and who have published that in the 2019. So if you look at the curve before, we have the trend. So I'm so fortunate to have colleagues who have been doing that work right at the beginning of the trend. So I will give you 2 examples. One is the work about the 5, which is developed by Mo. The other one is by Molu and about the permutation feature importance. So hats off to them so that I can build the work on top of their work. So after the comparison, maybe you would like to know what's more about the X-FIPE. Why it scores 6 in this slides and the other scores 4, for example, the SHAP part. So let's dive into the X-FIPE part. So first of all, I'll give you we have the comparison over here. The 5 took about 5 minutes, SHAP about 30 minutes. So how about let's compare the 5 and X-FIPE. So in this case, we are using more than 8 million records and a few hundred features. The time it took for 5 is about 3 hours, 191 minutes, and for X-FIPE, it's 15 minutes. So underneath the hood, you see, oh, that's just about 10 times faster. It's a little bit more than that. So it is computationally efficient because it reduces the time from capital O(n) to O log n. So why that's the case? Since we are doing everything in PySpark right now, and we can use the distributed or the parallel processing underneath. So one of the operations which takes a lot of time for FIPE is a combination, combining the data frames. Just like we have learned the merge sort in computer science about algorithm and data structures. If you do that one by one, for example, you want to combine here I'm using n is 64. If you combine all of them, first you combine the first 1, 2, and the 1, 2, and 3, 1, 2, 3, and 4, all the way, it's a linear. That's n. So this time, if n is 64, that will be 63 for each of the time. How about we do that a little bit cleverly? And it is triggered by a colleague when he is having a coffee break with my manager, and they have this conversation. He said, "What are you doing?" I'm waiting for the FIPE to finish. There's a better way. And he get back to work and use his knowledge of the data structure and the algorithm to figure out, yes, we can do that. Essentially, instead of merge 2, we can extend that to merge k. So for each case, we combine 2 together, 1, 2, and 3, 4, and n minus 1 and n. And the next layer, we do the 2 poles, 1, 2, and 3, 4, and then along the way. As you can see, instead of doing that in a linear, about the height of the tree, we are doing that in a log n fashion. So that improves the speed dramatically. So that makes our model be able to serve, make us to be able to serve the model in production. The second part I would like to highlight is about novelty of the X-FIPE is theoretically sound. So what I meant by that is I would like to focus your attention to the equation I copied from the paper of Sharp. On the lower left, the equation 4. So one factor of that is the factorials. On the second term is the f is s union the term you would like to, the feature you would like to get, the ith feature, and you get that value and you minus the f without the ith feature. And also, what's more important is about the kernel or the PyX using in the Lime fashion is if you are using this a specific kernel, you can get Lime for free by doing Sharp. So one of the factors, if you look closely, is a factorial. So we have factorial of f. Here's f is the total number of features, and the s, the absolute value of s is the length of the kind of the size of the feature you would like to choose from, and then the f minus s and minus 1, and you want to get those two factorial, and then the factorial of f, and then you multiply the delta between the f with I and without I. So look a little bit closely. Actually, that is hinted in the paper of Sharp, but I did a little bit more than that. Here on the lower right, I plotted 3 things. Each of them are using the feature f is 10, 20, and 50. I could plot a lot more, but that's even more dramatic in terms of if you look at the coefficient. So on the x-axis is the size of s, and the y-axis is the relative size of the coefficient. Normalize that using the lowest one. Essentially, the lowest one is 1. The highest one is the ratio between highest value and the lowest value. Look at the first one. If we are using 10, so lowest is around 4 and 5, because at 5 is the lowest. And on the side, 0 and n minus 1, or f minus 1, here you see 120 plus. And the second term drops dramatically to 20, the third even more, and then fourth, fifth, the smallest one. Let's focus, if the feature size is 10 or less, you don't really need a feature importance because all of them are important, or you can just hand pick of them. It's pretty easy. The value of the model explainability or the kind of top driver comes in because you have a lot of features coming in. It's exploding. It's exponentially a combination. You cannot handpick first few and next few, and then you hope you get the right answer. So that's why the algorithms shine over here. Look at 20. On the first one, I saw 80,000. The second one, much lower. And then the third one, much lower too. And then you get almost flat around 1. And if you look at a little bit to the right, 50. The first one, 10 to the power of 13. Where's the second one? Less than 10 to the power of 1. And then the rest are almost flat. Essentially, all other coefficients in the equation 4 are relatively small, actually a lot relatively small than the value on the side, which means if you want to make the S smaller or F minus S smaller, you will get the largest coefficient. So that's how we did the X-FIPE. The X-FIPE, essentially, we don't use all the middle layers. We only use the first and the last part. With that, we get a very good approximation of the shape value, but using dramatically less computation. So here's one example from our use case. Here we have 3 features. One is the age. The other one is emergency department visits. And also we have a utilization count. You saw those similar features in the example on the top drivers as well. So on the yellowish lines, so I have the coefficient 1/3. In the middle is 1/6. And the last one is 1/3 as well. So let's go over that from the very beginning. The very beginning is we use a foundation where we start from, where here we use the median for numerical values and our mode for categorical values. That gets us to a 0.2. And if we add age alone, that actually gives us 0.12. And we added the ED visit and the utilization count, that gives us 0.73 and 0.61 respectively. And then how about if we combine 2 of them? So we know there are only 3 combinations of 2 out of 3. So that's age and ED visit, that's 0.55, and age and the utilization count is 0.27. And the ED visit and the utilization count, that give us 0.9. How about if we have all 3 of them? There's only one combination of 3 out of 3. That's all of them. That give us 0.95. So in the X-FIPE part, we only consider the yellow lines. The coefficient is 1/3. In the shape sense, they consider all the edges. So that's just a 3. If we have more, that will be more dramatic for the reduction of the computation. So that gives us a linear compared to an exponential. I know there are efficient ways to compute the value, shape value for trees, but for others, there's just not a better way. To do that, we only need to use approximation. Our approximation, based on our experiments and our use cases, is a pretty good one. So here I can give you a walkthrough of that and how the X-FIPE works. Simple, 4 steps. First of all, so we have a model score. See, the ID is 1, 2, 3. That's a 3 people or 3 members. And we have the age and the ED visit and utilization count for each one of them. And also we have the prediction in the last column. For the first step, I will use only ID 1 as an example. So if you see on the first one, we only have 1 row, but the second one, we have 1, 2, 3, 4, 5, 6 rows. The reason being that we are doing a few things. The few things we have done are in the step 3. See the equation there? It's the SC and the SM, the S0 and the SX. The X0 or SO sub-0 is the original. Essentially, we don't change anything. That will be the first line in the step 1. The SX is a part where we only change x to its median or mode value. The s sub m is one we change everything to its median. That will be the first node up here. That's the median, the point 2 over here. And the SC, the complement, essentially only everything is set to median except x. So that's why we call that a complement. So the equation for that is the C minus M plus 0 minus x. So you plug in the equation, you get that result. You get the age, the ED visit, and the utilization. And the last step, you can rank. Depends on how you want to do so. Either for a positive impact, you can rank them, or the absolute value, you can rank them, no matter the either positive or negative. So you give it 1, 2, 3, so that you can act upon all. Typically for our use case is we output top 5, top 10, or more, depends on the use cases. And the one thing I want to share is the X-FIPE can be coded up pretty easily, just a few lines of code. So you from X-FIPE, import X-FIPE, and then the first line is, and then you build the X-FIPE object. Using object, you input a few things, the predict probability, which is a function on any either PySpark or Python model. And the model type, you can specify is a Python model or a Spark model. And then the feature list you want to rank, and also the score column names, kind of your target. And then the next line is to compute the SC, and then the SX, and then the XSO, and then the last one S sub M. So that's the median score, the original score, the X median, and the complement of X median. And the last step, you can just call X-FIPE the object with the calculate the feature impact with all the intermediate results. You get the last one, and then with those X-FIPE values, you can rank whatever you want, and then output those to your business stakeholders and discuss, and if that's an important one. So I want to emphasize that one because I want to let you to know about a few things before you go. So the first one is about the interpretable machine learning book. It's an online book. It's a great one. It has a lot of content standard in that. It's an evolving one. So I learned quite a lot as I was reading a few years ago and also today. And the second one is a survey about the methods, about explaining the black box models. Third one is about the is kind of give you a concept of taxonomies, opportunities, and challenges about the responsible AIs. The fourth one is a curated list of awesome machine learning interpretable resources. The last one is the one I just mentioned in the last one because I want to let you know the model explainability does not equal to causality. So that's why I created this tiny URL called not causal. It is actually written by colleagues of Lunenburg, who's the author of SHAP, and his colleagues in Microsoft Research. He wants to emphasize a few things. Don't take our SHAP value as the fact. You take that with a grain of salt because there are unmeasured confounding factors and unobserved and observed confounding factors. So talk with the subject matter experts, so that you know what you delivered about the top drivers align with their expectation. Sometimes it is, we all run into similar situation. It is statistically important, but not necessarily business important. So we have to align with them because we only observe data. From the data, we draw the inference, but the underlying logic, how the data was generated, lies far beyond our model can do, since our model only captures a subclass of all the possibilities of the family. So a few things I want to go with is, first of all, answer the two questions I have mentioned in the beginning. Are you ready to put the model explainability in your workflow with a computationally efficient and theoretically sound method? The other one, if you want to make an impact, have the value created, and you need to convince your business stakeholder to adopt that. I think on the keynote or others, we saw those. A lot of them did not go to the last stage. So we know we put a lot of effort in that. So we'd better to make the last mile, which is put the model into production. So with this model, we have the model explainability methods. We have a common vocabulary so that we, as data scientists or AI researchers who develop models or research methods, and with the stakeholders who will ultimately adopt our model to serve the customer, so that we can have a common language to communicate. With this model explainability methods or any methods, we have a bridge to bring the gap together. So I would like to also meet the team. So Max developed the kind of the O-login methods and also the implementation. I did that as well. Our manager, Steve, also bring more business use cases on that, and also the coffee break he had with Max. I will stick around for a few minutes for questions. We have 4 minutes here, and after that, I will be able to stay outside to answer questions as well. So thank you all for coming. Any questions you have? Yes, sir.
Being a first-order approximation, can you comment on the accuracy versus explainability trade-off?
Yes, the question is, you are using only the first order, how good it is. I have slides for you in the appendix. So this one explains a little bit deeper about each terms. So the M is see the subscripts. The subscript is the feature, the first one, the second one, the third one. The M on the top, the suffix is subscript is the medians. The sub M is everything is in median. The SC is everything except X, the one you're interested in, X1 here is. The SX, this one case is only X1 has median. Everything else is kept the same. The S0, the original. The equation, look at the 2 arrows here. The first one, the S sub M minus S sub C. The only difference between those two are the X M and X itself. So that takes care of the first term. And the last one is everything is the same except X is the median. So we take the other one. So essentially we take or N minus 1 or in this, let's say using the F, the total number of features, minus 1 with everything we have originally, essentially the F. So that's the S sub X minus S0. How good is approximation is? Here it is. We have done a top 5 using different methods like a top 5 and the SHAP top 5 and the X top 5. On the 5 part, it's doing pretty well. 4 out of 5. How about the X-FIPE? 5 out of 5. We have done a lot more on that. So basically the X-FIPE and the SHAP. So in terms of the top 5 part, we match pretty good on the all matches, 1 mismatch or 2 mismatches. And also if you look at that in the top 10 sense, so if they are not in the top 5, in the top 6 to top 10. So even they are not exactly the same for the top 5, they agree, you can find them in the other top 10. So our approximation is pretty good.
Just on that, similar to SHAP, does it also suffer from the issues of having to retrain if new unseen values exist within the data set? So if you want to do a new prediction and you haven't seen that value before, you have to retrain with that value.
I see one more time, please, sir.
So similar to SHAP, does it also suffer from the issue of having to retrain if a new unseen value exists within the new data set?
Our case, I think, a little bit robust on that part. Yes.
Does it take the median or the mode, because that's the approximation? Or?
Correct.
Yeah.
Correct. You're right. So So by taking the kind of the average here, we use the mode and the median. It is pretty robust. Kind of if for some of the features you do not observe before. So for other cases, it may be a little bit kind of fluctuate a little bit more. But this case, our experiments and the use case have found that it's pretty good actually.
And lastly, when can we expect the release of X-FIPE in the open source community?
This one actually is already ready last year. We have been pushing for our IT and a branding company to have a dedicated site for the open source community. We have tried to make that ready for today, but fortunately we have gone through 3 out of the 5 steps. I have that on a ServiceNow ticket, so it's not yet ready. I think the best way to find that in the future is just Humana X-FIPE, and then you will find that. I will go back and push them to so that we can publish that faster. Thank you, sir. Any other questions? Time's up, so I can stay outside for a few more questions. Thanks for everybody for attending.